Okay, so now we have Zeyu Liu from UCSD to give an introduction to rigid-analytic geometry.
Yeah, thanks for the introduction. So in this talk, I will talk about rigid analytic geometry. It will consist of two parts. First, I will introduce rigid analytic space over K, and then I will talk about analytification and Reynolds generic fiber function. And then I will explain why this Tate algebra has many non-split finite detail extensions. So let me fix some notation first. In this talk, we will work with a non-Archimedean field K. So let me introduce the definition for that. A non-Archimedean field is a field which is complete with some norm. And we want this norm to be non-Archimedean absolute value. In other words, this norm satisfies the following properties. First, the norm of x is 0 if and only if x is 0. That's why it is called a norm, not just a semicolon. Secondly, we want that the norm of the product of two elements is the same as the product of their norms. Most importantly, we want the strong triangle inequality code. In other words, we want the norm of the sum of two elements is bounded by the maximum of the norm of this x and y. There are several examples for such non-Archimedean field K. So the most common example is that K equals to Qt or a finite extension of Qt. And you can also think K as a Laurent series over Fp, something like that. Or the Laurent series over C. Most of the materials in this talk will work for all of such K, but some results or theorems only work for some non-Archimedean K with a discrete variation. I will highlight this one necessary. Any questions so far? Okay, so maybe before I introduce rigid analytic space over K, let me first explain that why the naive definition of n-dimensional manifold over K doesn't work very well. So you can guess what's the naive definition for n-dimensional manifold over K. So x over K is called n-dimensional compact manifold if the following holds. First, x is an analytic variety over K. Then we want x to be compact as a topological space. Finally, we want that at each point, the dimension is A. Let me explain this notation roughly. So, if you have an open set which is contained in K, then you can define analytic functions from U to K by requiring that locally at each point, in a neighborhood of each point, it can be written using Taylor series. Then by gallooning such functions, you can get the Euler definition of analytic variety. This is like what we do in differential geometry. And then you can get the Euler notations in differential geometry work very well. For example, at each point, we can talk about its tangent space, we can talk about dimension. That's why such definition makes sense. So this is the definition for n-dimensional compact manifold. So given such definition, the following theorem from Serre tells us the following. Okay, maybe let me fix some notation first. So in this talk, I will use O to denote the range of integers in K. It consists of those elements whose norms are bounded by 1. And we assume that n, which is contained in O, is a maximal ID. I will use the little k to denote the residual field. Then a theorem of Zeyu tells us the following. If k is a discrete value, in other words, you want this O to be a discrete valuation rule. And we assume that the cardinality of this residual field, the small k, is finite. So we use Q to denote its cardinality. Then there are only Q minus 1 many isomorphic classes of compact n-dimensional manifold over K. So roughly speaking, Zeyu proves that every compact n-dimensional manifold is isomorphic to the disjoint unions of Bn. Bn are balls in Kn, so it consists of those x1 data up to xn whose each coordinate has now bounded by 1. And it also proves that if you consider R copies of disjoint unions of these balls and R prime copies of this disjoint unit balls, then they are isomorphic as a n-dimensional compact manifold if and only if R equals to R prime modulo k minus 1. That's why we only have so many isomorphic classes. So it's not very interesting to use this naive definition. So we really need some new idea to work in rigid analytic geometry. Classically, there are several approaches for rigid analytic geometry. Today we will talk about rigid analytic space, which is mainly due to the work of Tate, but there are some other related notation methods like Reynolds formal models or Berkowitz space or Huber's adic space. So these 4 approaches are the main approaches in rigid analytic geometry. Okay, so that's all. Any questions so far? No question? Okay, so let me introduce rigid analytic space. I want to draw a picture like this. In classical algebra geometry, so suppose you work with schemes over C, then how do you work? So first you study the full subcategory of affine schemes. But how do you build affine schemes? You can start with some finite type algebras over C. But the building blocks for finite type algebras are polynomial algebras. Now we will play a similar game. So we want to obtain rigid analytic space over K. Let me just call it rigid spaces. How do we build rigid spaces? They are obtained by gluing affinoid rigid space. So you should view affinoid rigid spaces as an analog for affine schemes. How do we build affinoid rigid space? We use some affinoid algebras. But the building blocks for such affinoid algebras are just Tate algebras. So Tate algebras should be viewed as an analog for polynomial algebras in these rigid spaces theory. Okay, so for that reason, let me define Tate algebras first. The rough idea is that Tate algebras will be functions on the unit disk. So recall that if we work over C, every function on the open unit disk can be written as f of z equals to the sum of a(n) z to the n, where z is a constant here. A(n)s are some complex numbers. And if you want it to be defined in this whole open unit disk, you need to give some restrictions on these coefficients, guaranteeing that it converges. Now, if we work with rigid analytic geometry, if I have some function ft equals to the sum of a(n) t to the n, where a(n) are coefficients in K, then it turns out that the condition to guarantee that it converges on the closed unit bound. So this bar will be denoted as B1. This is a closed unit. Let me remark that this bar is also open because of the strong triangle inequality we mentioned. So this closed unit bound should be viewed as an analog of open unit disk over C. And then you can verify that this power series converges on this closed unit bound if and only if the limit of a(n) equal to 0, or equivalently, the limit of their norm equals to 0. Because you can equip this K with a topology. So to say that their norm converges to 0, it is almost the same as saying that they converge to 0. Okay, so any questions so far? The reason for that is it's not very hard, as you can see. If you consider the sum of a(n) tn for n ranging from k to infinity, now we know that this norm, you can roughly imagine that this is bounded by the maximum of n. If you restrict yourself to the closed unit bound, so you can imagine that this t is of absolute value no larger than 1. That's why it is bounded by maximum of the absolute value of A. So if you want this series to converge, it suffices to guarantee this condition holds. That's the reason. Any questions so far? Yeah, go ahead.
So, like, is k going to be discrete to the value, or is this?
No, sorry, I forgot to say that for this definition, we only require this k to be non-Archimedean field.
Sorry?
No, we only need this k to be a non-Archimedean field. We don't require these three values. Yeah. Any other question? Okay, so this is a case for, so in general, we can define. So let me give you the general definition. For n to be at least 1, we can define the n-dimensional, the n-variable Tate algebra over K is Tn. If I want to highlight the row of this K, I will just write Tn of K. It consists of those power series Aj x to the j, such that as j equals to infinity, the norm of Aj tends to be 0. So j is a multi-index. And we define the norm of j to be the sum of each component. So an x to the j really means x1 to the j1 that up to xn to the j. So here x1 that up to xn are coordinates. So this is a general definition for n variable Tate algebras. And it will be denoted as angle bracket T1 and T2. This angle bracket really means that you consider polynomial algebra with these many variables, and then you consider its P condition. So you get this Tate algebra. So from this definition, as we argued before, you can see that P and K is nothing but the subrun of the n-dimensional Hall series such that it converges on R A. Or I should say O A. Because that O is a variation rate. Any questions so far? No question? Okay, so let me give you some examples. If K is QT, we can consider this a many variable Tate algebras. And if K is CT, you can consider this one. So both of them are well defined as functions. Both of them could be viewed as functions on the n-dimensional unit ball in CP. In other words, it consists of all the elements x1 that are up to xn such that xi lives in CP and the normal xi bounded by 1. CP is a notation C, and it's used in yesterday's talk. So maybe I should say something about CP. Is a periodic completion of the algebraic closed extension of QP. Any questions so far? Okay, so a selected variant is the following. You can also consider, now maybe let me choose n equals to 1, and we consider the following. QP angle bracket x and x to the inverse. It really means that those power series, the sum of ai x to the I, where I ranges from -infinity to infinity, such that the limit of ai equal to 0 as the absolute value of I tends to infinity. So you require this convergence on both directions, when I tends to infinity or tends to -infinity. So this ring is larger than QP angle bracket x, right? And if you want to enlarge your ring, it should be defined on smaller locals. So the correct interpretation of this ring is that it could be viewed as functions on the circle. You can verify that this condition guarantees that it converges on the circle in CP. Any questions so far? No question? Okay, so let me state some basic properties of Tate algebras. As I said, they should be viewed as an analog of polynomial algebras, so they really enjoy a lot of nice properties. But before that, let me mention that we could equip a Gauss norm on these Tate algebras. So given f equals to the sum of aj x and j lives in T n of k, we can define its norm to be maximum of aj, or the norm of aj for all the multi-index j. This definition really makes sense. As you see, we required that the norm of this aj tend to be 0 as the norm of j tend to infinity. So this maximum actually is okay. It's not just a assumed, but actually is an actual maximum. And the following, so this is and you can verify that this really defines the norm of this T and K. So with this structure, given we could view T n of K is a Banach algebra. So if you are not familiar with the definition of Banach algebra, let me remind you what's that. So roughly speaking, if you have a K-vector space V, this V might be infinite dimensional, and then if you it is called a Banach space if you can find a norm on this V such that the following condition holds. The norm of V is 0 if and only if V itself is 0. And secondly, it satisfies the strong triangle inequality. And we also want that C, the norm of C times V equals to the norm of C times the norm of V, where C lives in K. So given these three conditions, you can say that this V is a Banach space. But in our case, actually T n of K is not a K-vector space, but it is also an algebra. So the last condition we want to make a Banach V K space into a Banach algebra is that we want it satisfies the following property. The norm of A, the product of A and B is bounded by the product of norms. So you can verify that if we define the norm on this empty variable Tate algebras in this way, then it satisfies all of these properties. That's why with this norm, it could be viewed as a Banach algebra. Any questions so far? Okay, so let me introduce another definition of norms on this Banach algebra. So for any point x in the k-bar point of this unit ball, we could, as we discussed before, we can consider the evaluation of f at x. So the evaluation of f at x really makes sense, and it is an element in k-bar. So from this, we can define a norm. This is only a semi-norm from T and K to k-bar as follows. We just send f to the evaluation of f at the point x, and then we consider its norm. So this defines a semi-norm on n-dimensional Tate algebras. And you can verify that. Oh, sorry, I should say that now you consider the composition with the norm on k-bar itself. Then you get something. You get something from the Tate algebra to R. Then you can verify that the Gauss norm we just defined is the sum of all of these semi-norms where x ranges from Bn k-bar. So it depends on how maybe you think this definition is a more intrinsic one. And there is actually a maximum modulus principle tells us that this can be obtained at some point x. But a key point here is that you need to let your x ranging over all k-bar points of the unit ball. If you don't use all of the k-bar points of the unit ball, for example, if you just use k points of this unit ball, then this might not be obtained. Any questions? Okay, so finally, let me list some nice properties of these Tate algebras. Do you need
the K bar
yeah.
for the soup equation?
I think for this you don't really need k-bar. It also works for k. Yeah. But if you want to get this maximum, you really need to work with k-bar points. Proposition Tn that has following properties. First, it is Noetherian, it is regular, it is a UFD. Secondly, every ideal I in Tn is closed. By closed, I mean closed with respect to the topology, with the topology determined by this Gauss law. And then we know that for any maximal ideal in Tn, Tn over n is finite over k. This property is very useful because we know k is a non-commuting field. Once you have a finite extension of it, you can extend the variation on k to this larger field uniquely. So figuratively, later when we have a affinoid algebra, so Tate algebras are a special type of affinoid algebras. When you have an affinoid algebra here, how do you build a space? Actually, as a set, you just consider M of A, which is defined to be all the maximal ideals of A. This is quite different from what we do in the scheme theory. Here, if you have some algebra to build affine scheme, you just need to consider all the prime ideals of it. But here, we need to consider all of the maximum. Any questions so far? And maybe last is that the k-bar points of the unit ball to the maximal ideal of Tn is surjective. So now you can find some key difference between this rigid space with what we get with our naive definition. So roughly speaking, to get a useful definition, to get something really nice, you need to consider not only k points, you need to consider actually all the k-bar points in some sense. This is what the last tells us.
How do you mean the last one?
You mean here?
Yeah.
Oh, this means the maximum ideals in Tn. Okay. Any questions so far? Okay.
The last statement is the equivalent to the first.
Wait, which one?
The last statement, that's the maximum k-bar points to maximum ideals is surjective. Is that equivalent to the previous statement?
Not equivalent, but just actually
It follows from the previous.
from which then?
The previous statement that the residual field at every maximum ideal is finite extension.
Oh yeah, it should be followed from this. So yeah, so we just need to k-bar, but not we do not need any completion. Question?
Yeah, so is this like a partial Molch-Down mass for Tn, sort of?
Okay, so I have finished the definition of this Tate algebra Tn, which should be viewed as polynomial algebras, and then we can build the general affinoid algebras from Tate algebras. So let me introduce the following definition. Okay, algebra A is an affinoid algebra if there exists some surjective map of algebras alpha from some n-variable type algebras Tn to n. So this is the definition of affinoid algebras. Given such definition, and the properties of these Tate algebras, we see that every affinoid algebra is non-zero because it is a quotient of a non-zero root. And we know that every finite generative, remark. First, and then we can define given such a presentation alpha, we can define a residual norm on A. By setting the norm of x to be the infimum of all of those y which maps to x on the alpha. A priori, this is only a semi-norm, but a property we just list here is that every ideal I in Tn is closed. And that's why if you define the infimum norm on A in this way, that this is actually a norm, not just a semi-norm. So now, any questions so far?
So does it take the norm depend on
That's you mean this norm depend on? Yeah, that's really a good question. This norm really depends on alpha. However, the topology it defined doesn't depend on alpha. In other sense, if you have two different alphas, and you get two different norms, you can show that these two norms are bounded from each other. So they define a same topological structure. Okay, so now I have finished the definition of affinoid algebras. So as we said, we want to get some functor from this affinoid algebras to affinoid rigid space. As I have told you secretly, as a set, this space we are going to consider is just M of A, the set of all the maximum ideals of A. But I still need to talk about topology and structure shape here, maybe. So next, let me say something about the topology. This M of A is the set of maximal ideals. So the distinguished open in the classical algebraic theory are denoted as D of F. So really, we want to get something similar to that. These are called rational subdomains. The definition is as follows. Let A is an affinoid algebra as default, and F1 that are up to Fn and G lives in A such that they generate the unit ideal. Then we consider the space X, which is defined to be the set of all the maximal ideals of A, and we define a following subspace of X as follows. So this is contained in a set X, and it's defined to be those X which lives in an M of A such that the evaluation of Fi at X are bounded by the evaluation of G at X for I ranges from 1 to A. This guy will be called rational subdomains. This condition roughly guarantees that for any x lives in this rational subdomain, the evaluation of g at this point x is not zero. Because otherwise, if g of x is zero, then all of them is zero. But the norm of 1 is not zero, so you get some contradiction. So based on such rational subdomains, we can consider rational cover. Now we suppose that F1 data up to Fn generates the unit ideal. Then xi, if we define xi to be x f0 over fi up to fi minus 1 over fi, then fi plus 1 over fi. Fn over fi. Then x is the union of all of those xi. Because for each point x here, you can compare the norms of fi evaluated at this point x, and you can pick a maximum. You can pick I such that fi at x obtains the maximum. So it lives in that xi. That's why you can always find such a union. So this is called a rational cover. Any questions so far?
Just for verification, you have x equals, right under where you start with the definition, you have x equals m of a, and then below it somewhere you have x is an element of m of a, such that what's going on between those two statements?
Between this definition and this?
The first one.
You mean here?
Yes.
What's the meaning of this sentence?
I'm just.
So sorry, here I should write f1 of g, f2 over g, up to fn over g.
These are two little different x's.
Yeah, okay, that's what I was thinking.
Small x.
Yeah, sorry about that.
Got it.
Okay. I don't think I have time to define the structure shape, but you could imagine that it just sends, the structure shape should send x to A, and it sends such rational subdomain to some affinoid algebra like this. It's a theorem of Tate telling us that this actually defines the shape. If you equipped with topology generated by rational covariance in this way, then it satisfies some shape property. Any questions so far?
Why do we use max spec instead of spec?
Yeah, that's a very good question. One of the reasons that we want to work with maximum ideals is that, as I said, if you consider the residue field at maximum ideal is a finite extension of K, so it can be equipped with a unique extension of the valuation on K. But if you work with a prime ideal, if you consider the quotient by this prime ideal is an integral domain, and then if you consider its fractional field, it's not necessarily finite over K. But there are actually more serious reasons, so you can read the book given by Bob. Yeah, later. Any other questions?
So I guess let's consider all the semi-norms on A. Then this MA embeds into the space of all semi-norms. And then you have a natural topology over there. Does this topology agree with that?
Agree to which topology? To the. Are you talking about for which space?
Yeah, it just seems like MA is just naturally so set theoretically there the conclusion matches perfectly.
Sarah, do you know?
Yeah. So I think it's a continuous match. Oh, so Zeyu took it. So when if you took the space of semi-norms, essentially Google topology in the set of points. And what Zeyu is saying is considering smaller subsets. That's a good point for both topologies.
in summary, if we have some affinoid algebra A, we can construct a topological space X given by, as I said, it's just all the maximal ideals of A, and it is equipped with a topology, and it has some structure shape. So this will be denoted as score of A, and so this is an affinoid rigid space over K. And rigid spaces over K are just locally ring spaces which locally isomorphic, which can be locally covered by such affinoid rigid space. So by gallooning such affinoid rigid space, you get the whole category of rigid space. But there are actually some subtle things about this topology, but I don't have time to talk. Okay, so next, I would like to talk about this analytification functor. Roughly speaking, the goal is to build a functor from algebraic varieties over K. To rigid spaces over K. So we want to explain how to construct such an analytification functor. So maybe the basic step is to deal with AKN, the n-dimensional affine space. So the rough idea is that if you have this n-dimensional affine space AKN, you should send it to the union of n-dimensional balls with radius r1, r2, and ri, such that as I increases to infinity, this ri tend to be infinity. So the union of n-dimensional balls with radius ri. So this is a rigid space. This is an affinoid rigid space, and you have to consider the union of this. So that's a rough idea, but let me make it more precise. So we can pick an element C living in K such that the absolute value of C equals to 1, and we consider, the absolute value of C is at least 1. So for example, if K equals to QT, you can pick C to be 1 over P. Then we define Tn of I to be Tn of Ci. This should be viewed as functions on the closed n-dimensional ball of radius C to the absolute value of C to the R. So we can write it more explicitly. It consists of those power series which look like this. You can imagine that C is just 1 over P, so this should just be P to the I over x1, P to the I over xn. So these are functions on the n-dimensional closed ball of radius. And then from this Tni, this is an affinoid algebra, we can associate it. We can associate an affinoid rigid space to it, which is denoted as score of Tni. And then so the relations we have is that Tn of 0. So as the region enlarges, we know that the rings should shrink. So we have this relation. But all of them actually contains the polynomial root. That's from the definition of this Tate algebras. And then we can consider Bn, which is just a score of Tn0, and then actually it embeds into score of Tn1. And then all of these are affinoid rigid spaces. Then you consider the union of these affinoid rigid spaces in suitable sets. And you call this the rigidification of the n-dimensional open space. And you denote it as the rigidification of IK. So our functor will send IK in to the rigidification of it. Any questions so far?
Can you tell us what are these TNs on the virtual?
You mean what are these?
No, the ones about you said TN0 and then TN1.
You mean what's the definition of Tn0, Tn1?
Right.
Oh, sorry, I have to say that Tni. Tni is functions of the n-dimensional closed ball of radius c to the r.
Oh, that's an I. Okay.
Yeah, sorry, there is an I.
Okay, thank
So,
you.
so as I said, as I enlarges this, radius enlarges.
Yeah, that I got. Okay.
Any questions so far? Now, actually, you can play a similar game. If you don't start with, if you start with now if you start with a quotient of, if you start with spec k x1 beta xn over alpha for some ideal alpha. In other words, if you don't start with a polynomial algebra, but start with a general finite type algebra, and then you can repeat this instruction. You can let, okay, so you can quotient by alpha everywhere, and then you can consider spur of Tn0 of alpha, and then quotient all of them by alpha, and then finally you get something like this. You call this the rigidification. Let me call this algebra. Let me call this algebra B. So you get the rigidification of spec B. Yeah. Any questions so far? But I don't think I have time to explain why this construction is reasonable. In other words, you want to verify that the rigidification of this alpha line actually satisfies some universal property. In other words, if you have any rigid space Z, and then a morphism from the rigid space Z to this rigid space is the same as choosing n global sections of the rigid space Z. So this would be the expected universal property. And I also, it seems that a priori this construction might depend on C, right? But actually it is independent. So you can do that by verifying some universal property that this rigidification functor satisfies. Any questions so far?
So it also doesn't depend on the specification of the ring.
Yeah, also doesn't depend on this alpha. Okay, so then let me explain what's a Raynold generic fiber functor. I have to be a little careful in this section. So from now, I assume that O is a discrete variation root. So the variation should be discrete, and we fix a uniformizer pi in O. So we would like to build a functor from. The goal is to build a function. Build a functor from the category of formal schemes. Let me set admissible formal schemes over O to rigid spaces over K. So SK is a SK is a generic fiber of O. That's why this functor is called Raynold, and it was studied by Raynold. That's why it is called by Raynold generic fiber functor. So let me explain the definition of the left category first. definition, a topological algebra A is called admissible if the following are satisfied. If first, A is topological of finite type, topologically of finite type over O. In other words, you can actually use curly A. This curly A could be written as the quotient by such Tate algebras over O by some ideal alpha. The definition of this ring is similar as what we did before. So now the coefficients are in O, and you require that at the index j tend to be infinity, the norm of aj tend to be 0. And most importantly, we want to add some flat condition. We want that this curly A has no pi torsion. So in other words, we want A is flat over O. Because you don't want to lose too much information by pulling back to the generic fiber. That's why you might want to add this flatness condition. Then given such a admissible algebra A, we can consider the following. So let's start from the Tate algebra over O. So we send spore of O T1 to Tn. So this I'm saying that this functor should send such formal scheme to nothing but just a Tn. Recall that Tn is just the generic fiber of this root. This was defined as a variable Tate algebra, but this is also just the generic fiber. And in general, if you have spore of such Tn over some alpha, it just sends it to this functor should send such formal scheme to spore of Tn over alpha. I'm using some wrong variables in this part. Maybe it's better to use x1 up to xn. Sorry for that. To keep the notation, should use x1 up to xn. And then you can glue this functor. Yeah, go ahead.
Is that inside the pi?
Yeah, the left hand side. So these are all topological algebras, and the topology is a padded topology. That's why I'll assume that this always discrete valuation first. So the topology is just a padded topology. You have to verify something to get this functor by gluing. For example, you need to verify that it's an open subset to open subset. Any questions? Okay, I still have 3 minutes, and then I will briefly explain that why CP angle bracket x. So this is just Tate algebra with one variable, many non-split finite electoral extensions. So let's x to be spore of CP angle bracket x. So this is an affinoid rigid space. So in this talk, the topology I defined should be viewed as an analog of the rigid topology. So this is called analytic topology. But actually, just as we can equip the category schemes with the rigid topology or étale topology, actually you can also consider rigid spaces, the category of rigid spaces equipped with étale topology. So you can talk about the étale side of this X. So to show that this guy has many non-split finite étale extensions, we will actually show that H1 of X with mu p is very large. So any non-trivial element here gives you a finite étale extension of CP angle bracket X which is a finite étale extension with Galois group mu p. So then you get some non-trivial stuff. So to calculate this guy, we need to use a Humo sequence like this. 0 to mu p to gm to gn. Here we send x to its p's power. So this is an exact sequence in the étale topology. I want to remind you that this map is only surjective if you work with étale topology instead of analytic topology. And then this implies that H1 étale x mu p will get some sequence like this. And the fact we need to use is that H1 étale x gm is 0. So let me briefly explain it. So this means there are no non-trivial line bundles in the étale topology. But there are some results saying that there are no difference when you talk about étale line bundles or the analytic line bundles. And because X is affinoid, so actually it has no non-trivial rigid line bundle. So it also has no non-trivial étale line bundle. That's why this is 0. So this is 0. So you get that this group is nothing but this group. And you can verify that this group has many non-zero elements. So but I want to say that you can compare this result. So if you don't work with angle bracket x, if you work with affine over Cp, if you consider spec Cp bracket x, and then if you calculate mu p, similarly you can get that this is the same as units in Cp bracket x quotient over Cp bracket x unit to the p's power of this unit. But the thing is that this group is 0, as you can verify that the unit in Cp bracket x is nothing but just the units in Cp, and every unit in Cp can be written as p power of some other elements. So that's why this guy is 0. So you couldn't get any non-trivial finite étale extension of Cp bracket x. However, the story is quite different if you work with this Tate algebra. You really get something interesting. Okay, I want to end my talk here. Thank you.
Is there a Gaga theorem in this context?
Yeah, there is a Gaga theorem. There is a maybe this functor is also called Gaga functor.
Can you give us an example of a power series that is in
Yeah, that's a good question. So I'm thinking about maybe I think 1 plus pt is such an example. Sarah, do you think so?
Think about it. What PT might be.
1 plus pt might be something living here but not living here.
Maybe just a smaller power.
A smaller power.
Okay, the 1/billion.
Yeah.
Was it important in this combination that you took mu p rather than mu L?
I think for mu L you should get 0, right? Yeah. So that's, yeah. I forgot to say that if this is not mu p but mu L, you will get 0.
Any other questions?
Thanks.
I just have to stop the recording.